All right, so I think we can start right now. Hello, everyone. I'm Tanya. We've met in the last introductory session. So I'm pursuing my PhD in flight mechanics and control, and today we'll go over some questions from aircraft stability and control. All right. So so today we'll just see longitudinal static stability and its control. Okay. Uh, so before we start, I'll just recap some of the equations that we had either derived or gone through in the last session, and some concepts that will just help you to solve the questions. So first we had seen what an aerodynamic center is. So initially we had seen that the aerodynamic forces, act about a point called center of pressure, denoted by Cp. And since this center of pressure keeps changing throughout the course of the flight, that is, it changes with angle of attack, it becomes difficult for us to perform analysis. And so we introduced a point called aerodynamic center, which is independent of angle of attack. So it remains the same throughout the flight duration and makes our analysis easy. Then we saw what trim was. Trim is a equilibrium condition for the aircraft, which is essential to analyze stability of any system. So for the aircraft, it's called trim, where the net forces and moments are zero. Then our pitching moment convention is nose up pitching is positive, nose down is negative. All right. And then we have the basic equation for pitching moment, the linearized equation for pitching moment, which is given here. Cm is Cm naught plus dCm by d alpha into alpha. And the only condition for longitudinal static stability we had seen last time, the only condition is that the slope of this line must be negative. All right. So it should be just a minute. So if this is your Cm versus alpha, your slope should be negative to ensure stability. That is the only condition for longitudinal static stability. Another condition that we saw is the Cm naught should be greater than 0. This is just to ensure that you can trim your aircraft at positive angles of attack. We had seen two ways to ensure Cm naught greater than 0. Does anybody remember? Can you recall and let me know what were the two ways to ensure Cm naught greater than 0? Positive CMAC, yes. For that, what kind of airfoil will we use? A reflex airfoil, right? So we had introduced this concept. It was the reflex airfoil. All right. Okay. So let's just move ahead. It's taking a while. Okay. Yeah. So these were the main equations that I think we had derived in the last class. So these are just the main equations that will be useful for your numericals. So the first one is the wing contribution towards Cm, towards pitching moment. This is towards the Cm naught contribution of the wing. This is the Cm alpha contribution of the wing. Now for stability, we only have to look at the Cm alpha part. Similarly, for the tail, we have Cm naught of the tail, and this entire thing, including the negative sign, is the Cm alpha contribution of the tail. Then you have a neutral point. Neutral point definition was just like aerodynamic center. So aerodynamic center is for aerodynamic surfaces like wing, tail. Neutral point is for the entire aircraft. That is the only difference. Then we had seen static margin. What is static margin? It is a way to measure the stability of the aircraft. So it's the distance between the neutral point and CG. Greater the static margin, greater is the stability. All right. Just some more equations. They're just expansions of the terms that were there in the previous equation. So downwash angle epsilon naught and the slope of the downwash angle d epsilon by d alpha. It's given by this formula. Then you have VH, which was the horizontal tail volume ratio. So it is STLT upon SC bar, where LT is the moment arm. And another point that you need to remember is that there's a difference between the lift coefficient of a 2D airfoil and of a 3D wing. This difference was due to the wingtip vortices. We had seen this in the last session when we had discussed about aspect ratio. Alright, so this is the relation between the CL alpha, or the lift coefficient, lift curve slope of a 2D airfoil and a 3D wing. Alright. Yeah, so let's start with the questions. The first question is, in an aircraft, without changing any other dimension, the distance of the aerodynamic center of the tail from the CG of the aircraft is increased. The longitudinal stability of the aircraft will increase, decrease, remain same, or you cannot say. You can just refer the equations that we had seen. So what is the term that is changing? It is the aerodynamic center of the tail to CG. How do we denote that term? It is LT, right? The moment arm. Yes. So if your LT is increasing, will the longitudinal stability increase or decrease? Okay, so Parthiv says increase. Does anybody? I got two answers which say increase. Increase is the right answer. So what was the CM alpha part? CM alpha of the tail. The equation was something like minus VH eta CL alpha tail 1 minus dou epsilon by dou alpha wing. Yeah. So where do we find LT here? In the VH term, right? So VH is ST by S, LT by C bar. So now when this LT increases, the entire term becomes more negative. When it becomes more negative, it means that the aircraft is more longitudinally stable. So the right answer is it increases. With the increase in LT, this VH increases. So the entire term becomes more negative. The slope becomes more negative. So the aircraft is more stable. All right. Next question. If the distance between the aerodynamic center of the tail and the CG of the aircraft, same quantity, okay? If the distance between the aerodynamic center of the tail and CG of the aircraft is reduced by 10%, what will the new area ratio, ST by S new, be in order to maintain the same tail volume ratio? So VH for the two cases should be same, and your LT is is reduced by 10%. So what will the new ST upon S ratio be? So our formula for VH was VH is ST upon S LT by C bar. Now this LT is decreasing by 10%. VH is remaining same. How will this change? That is the question. Try doing it. Take a minute or two to solve this. B. Okay, I already got an answer. B. What about the others? Two of you have gotten B. I'll just wait for a minute for the others to catch up. Okay, so let's just try solving this together, okay? So this was your VH formula. So let's just say VH old is ST upon S old into LT old. C bar is the same, so I'm just going to, and let's divide the whole thing. So let's just do it properly. And you have VH old and VH new are the same, right? So you have ST upon S new into LT new, correct? So now this VH is the same, LT is reduced by 10%, right? So VH old and VH new are the same. How do we equate these two equations? So it will be ST upon S old into LT old is equal to ST upon S new into, it's reduced by 10%, so it's 0.9 LT old. So yes, the two of you who've gotten, will it be C? It's reduced by 10%, right? So it will be 0.9. Two people have gotten B, so yes, the correct answer is B. Alvin, why did you change it to C? Oh, okay, they've asked you for the new ratio. Yes, yes, yes. Okay, yeah, yeah. Sorry. They've asked you for ST upon S new. Yeah, so it is, my bad. Yeah, it is C. Correct. They've asked you for the new ratio. All right, all right. My bad. Yeah. So it is 1 by zero point 0.9. You're right. Option C is right. Okay. All right. Let's go to the next question. Okay. During the flight, if the elevator is deflected with a certain positive angle, how will this affect the stability of the aircraft? Remain same. Okay. Okay. Can you give me a reasoning as to why it will remain same? CG won't change. Okay. Correct. So elevator is a control surface. It is used to control the aircraft. It is not. Yes, CG won't change due to elevator deflection. Correct. So elevator is a control surface that is used to navigate or control the aircraft. It doesn't change the inherent stability. So it doesn't change the slope of the CM alpha, right? CM versus alpha curve, the slope doesn't change. The elevator deflection does not change the slope. So it doesn't affect the stability in any way. No deflection of any control surface changes the stability in any way. Alright, so the correct answer, yes, it does remain same. So now that we have introduced control, so we'll just go over some concepts of control and some basic equations that will help us with the next questions. Alright, can you give me the question or you can put up the question? Can you give me the question? I don't have the question with me. Maybe towards the end of the class, we can have the question. Try to get the question by then. Alright, so let's just continue with this one now. Yeah, so control, we're just introducing the concept of control. What does control do? Uh, it is trimming the aircraft at different CLs. What does that mean? So, as of now, you're trimming the aircraft at a given CL. So, you have CM versus CL, and your graph is something like this. So, this aircraft is getting trimmed at this CL. So, now you want to suppose you reduce the CL trim. You want to trim the aircraft. What was trim? Trim is equilibrium, right? So, you want to trim the aircraft at a different CL. Suppose you want to trim it here. Then you deflect your elevator control surface in such a way that the graph is shifted. it does not change the slope. It merely translates the graph. Your CM versus CL graph is just translated over the axis. It doesn't change the slope. So does CM not change or does CM alpha change? What changes? CM naught, correct. So only the CM naught changes. It doesn't change the CM alpha. Hence, the control doesn't affect the stability. All right. So our convention is deflection of elevator down is considered positive. Why is it considered positive? So if I take this to be the fuselage reference line and this to be my tail, and if I deflect the elevator downwards, it produces a increase in lift. There is a delta L. Delta L is positive, correct? So delta L is positive, and this is the reason why deflection of elevator down is considered positive. All right. So similarly, this suppose your CG is somewhere here, and this increase in lift contributes towards a pitch down or pitch up. This delta L, if I deflect my elevator down, it creates a positive lift. That positive lift creates pitch up or pitch down. Pitch down. Okay, so that is why your CM delta has a negative sign here. Alright, CL delta is because you have a positive, for positive deflection of elevator, you have positive lift. Similarly, for positive deflection of elevator, you have negative pitching moment, which is why you have a negative sign here. Alright, we'll come to the question towards the end of this, alright? We'll try to solve it. If not, the next session we'll solve it. Okay, so delta E trim, that is how much we need to deflect the elevator to trim at a given CL, is given by this equation. All right, so this we will be using in a few questions. So just try to remember this. This is your y-intercept and this is your slope. Now from this equation, will the graph have a positive or negative slope for a stable aircraft? So if your graph is delta E trim versus CL trim, will it have a positive or negative slope? Negative slope. So it will look something like this. Alright? Because your XNP minus XCG for stable aircraft is positive, CM delta E is negative, hence your slope is negative. Alright. Now let's move on with the questions. Okay. With the increase in static stability of an aircraft, the elevator required for a given CL trim will be more, less, same, can't say. So I will just draw the graph. The equation is the equation that we saw in the last slide. So I'll just draw the graph to help you understand. Delta E trim. This is CL. Okay, so this is the nature of the graph. From this, can you try to answer this question? With increase in static stability, the elevator required for given CL trim. I'll just write the equation that might help you with solving. So this is the equation, this is the graph. With increase in static stability, does delta E trim for same CL trim, does it increase or decrease? Or you can't say. Okay, so one answer is less. What about the others? Same. Okay, what about the others? CM naught remains same, yes. If I deflect the elevator, CM naught doesn't remain same. So this question, they've asked you how much will the elevator deflection change. So CM naught is anyway not remaining same. CL trim remains same. Okay, so they've said for a given CL trim. Okay, so now look at the equation and tell me that if I increase the static stability, will the slope increase or decrease? Slope increases, correct? So the same graph will look something like this. Now suppose, let's just take it at this CL trim and draw a vertical line. So this is 1 and this is 2, and 1 is more stable than 2. All right. So now I take at this CL trim, let's do the analysis. For 1, your delta E1, and this is delta E2. So we can see that delta E1 is less than delta E2. So now what is the answer? It is less, right? When the stability increases, the delta E required is less. Correct? I hope this is clear. So when the stability increases, slope increases. So you draw the two graphs and at the same CL trim, do the analysis. We can see that the delta E required is less. Even intuitively, we can guess this, right? So when the aircraft is more stable, I need to deflect the elevator less to trim it at the same CL trim. If you think about it intuitively, it gives you the same definition, right? All right, so let's go to the next question. Yes, trim elevator deflection remains same with increase in stability. That was the question, right? So trim elevator deflection does not remain the same with increase in stability. It reduces. Was that not clear? Like, let me just go back to the previous slide. That is the exact same question, Parthiv. So what we had seen is with the increase in static stability, the trim elevator deflection is required as less. We need to deflect the elevator less to trim the aircraft at same CL. All right. Okay. So let's move on to the next question. Here we have some data given to us, and then you have a set of questions for the same data. So let's just read the data carefully. The wing, fuselage, pitch and moment characteristics of an airplane. Okay, so for the airplane, the wing, fuselage contribution of pitch and moment is given here. So this is the Cm naught contribution of the wing fuselage, and this is the Cm alpha contribution of the wing fuselage. Okay, where alpha is the angle of attack, W and Fs refers to wing and fuselage. Then they've given you SW, which is the wing area, and the wing characteristics. Span of the wing they've given, mean aerodynamic chord, X bar CG, aspect ratio of the wing. Then you're given the lift characteristics, CL. CL alpha of the wing fuselage. The slope of the wing fuselage in per degrees. Be very careful of the units. Then they've given you IW. IW is the wing setting angle. That is the angle at which the wing is fixed on the aircraft. Then you have CL alpha 0. What is CL alpha 0? What is that quantity? at alpha equal to 0, what is the lift? What is the lift coefficient, right? Okay, so this means that it is a cambered airfoil. It is not a symmetric airfoil. For a symmetric airfoil, CL at alpha equal to 0 is 0. Okay. Then they've given you the horizontal tail characteristics. They've given you the moment arm, aspect ratio, efficiency factor, and the slope of the lift curve slope of the tail. Again, it is in per degrees. Now let's look at the questions. Now, question is, it is desired to have the complete airplane pitching moment characteristics. That is, what is given to you is the contribution of the wing and fuselage. What they have told is that the entire aircraft should have, that is, wing, fuselage, and tail contribution should be this. So, what is CM not tail? What is given to us? Is the fourth option not visible? So, fourth. I don't understand why the fourth option is not visible. So it is 0.1, 0.2, 0.3, 0.4. Okay, those are the options. Right. So what is given to us in the main data? You have CM naught of wing and fuselages minus 0.05. In the question, we have CM naught of wing, fuselage, and tail is 0.15. Now try to tell me what will the answer be. Okay, we've gotten one answer already. Okay, what about the others? It's always only these two who are responding. What about the others? Do stop me if it's confusing or you don't follow it anywhere. Right? At any point, if you don't follow it, please do stop me. We can go over it again. I'm only getting answers from two students. What about the others? So they've asked, what have they asked in the question? CM naught contribution of the tail. They've given you the whole contribution and contribution of the wing fuselage. They've asked you about the tail. So it's a simple subtraction, right? Okay. So all we have to do is 0.15 minus of minus 0.05. You get 0.2. Correct. Okay. So now look at the complete aircraft characteristics and can you tell me if the aircraft is longitudinally stable or unstable? Why is it stable? Correct. Perfect. Negative CM alpha. Right. Okay, now let's go to the next question. Okay, next question is, what is the contribution of horizontal tail CM alpha? In the first question, it was contribution towards CM naught. Here they've asked you contribution of CM alpha. Again, I'll write down what we have. CM alpha of wing fuselage is minus 0.0035. CM alpha of wing, fuselage, and tail, what was given in the question, is minus 0.025. And they've asked you CM alpha of the tail. All right, we've gotten one answer. What about the others? It's just, again, it's just a simple subtraction, right? I hope the others are following. The answer is right. It is minus 0.025. 0215, sorry. Let's move on. Okay. The approximate value of dou epsilon by dou alpha, that is the slope of the downwash angle. Do you remember the formula? I will write it down here. when we solve a few questions, you will remember these formulas. It's not very difficult. It's 2 CL alpha wing by pi E AR. AR of the wing, okay? Be very careful of the units. Okay, we've gotten one answer. What about the others? What about the others? We'll just wait for a minute or two and then we can solve it. It's just a direct substitution of the values that are given to you. You just need to be careful of the units. Okay, let's just do it. You have 2 CL alpha of the wing is, here you can take the wing fuselage quantity. Okay, so that is 0.07 and it's given in per degree, so we need to, oops, what happened? Is the question still visible on your screens? Because on my screen it isn't. Okay, then I'll just wait for a minute for it to load. Alright, yeah. So this is given in per degree, so we need to convert it to per radians. So I'll just multiply 57.3 by the aspect ratio of the wing is 7.3 and then you have 0.35. Okay, I hope it's clear to everyone. Okay, yeah, so we've got a couple of more responses. Nice. The next question. Yeah, so the next question is the horizontal tail volume ratio, VH. So try to recall your formulae. Just take a minute or two to recall your formulae or refer to your notes, and then I'll give you the formula. We've asked you to find out the horizontal tail volume ratio with, just see what quantities you already have or you're already derived, and then you can try finding VH. Yeah, just look at the quantities you have already derived and see if you can find out VH through some other way. Tail area is not given, that is true, but there may be other ways to find out VH. Just see the quantities that you have derived so far in the previous questions and the quantities that are given and try to find another way to find out VH. Okay, I'll give you a hint. We had found out Cm alpha tail in the first or the second question. Using this, you'll be able to find out VH. So what was the formula for Cm alpha contribution of the tail? We had done this derivation in the last class. So I'll give you the equation. It's minus VH eta Cl alpha tail 1 minus dou epsilon by dou alpha. Now we have all the quantities except VH. So just rearrange the terms and try finding out VH. Okay, what about the others? Now it's just a direct substitution, right? You should be able to do it. What about the others? What about the others? Alright, so I'll just put up the values and we move ahead. So VH is uh, minus Cm alpha tail by beta Cl alpha tail 1 minus dou epsilon by dou alpha. And when you substitute, then you get 0.0215 by eta is 1. Cl alpha tail is 0.073. Both are in per degree. Cm alpha tail, Cl alpha tail, both are in per degree, so it doesn't matter. You don't have to convert the units. And minus, we have just found out 0.35. So yes, the right answer is 0.453. Okay, so let's go to the next question. Just give me a minute for it to load. Alright. The ratio of horizontal tail area to wing area, ST upon S. Now it should be straightforward, right? Now that you have all the quantities, even VH, this should be straightforward. The others, please try to answer as well. B, okay. What about the others? So let's just write down VH formula. It's very well known. You have ST upon S, LT upon C bar. We have VH, we have LT, we have C bar. So ST upon S is 0.453. We just found that into 1.24 is C bar and LT is 4.496 and you get 0.153. That is the right answer. Okay. Next question. The approximate value of epsilon naught in degrees. Okay, I haven't written that, but it's in degrees. Yeah. I hope you remember the formula. The slope formula we had used, it's similar to the slope formula. Try doing this. You remember the formula, it's a direct substitution. Again, unit conversion is necessary. Be very careful of the units. Okay. Alright, so let's just write down the formula. Epsilon naught is 2 CL naught by pi E AR. Okay, so that is 2 into 0.26 by E. Aspect ratio is 7.3. So here you get the answer in radians. Okay, so you get 0.022 radians, and we need to convert it to degrees. And 1.3 B, it is the right answer. I think a couple of you have gotten it right. Okay, let's go to the next question. Calculate the value of tail incidence angle in degrees required to achieve CM naught. So the hint is given in the question directly. You need to use the CM naught equation, CM naught tail. CM naught tail, the value we found out in the first question. Now use the analytical equation for CM naught tail to find out IT, tail incidence or tail setting angle. So you need to use the equation for tail contribution towards CM naught. hope you remember the equation. I'll write it down. Cm naught contribution of the tail is VH beta CL alpha tail into wing setting angle plus epsilon naught minus tail setting angle. Okay. So just substitute all the terms that either are given in the question or we have found out in the previous question, and you'll be able to get the answer. So we've gotten one answer. What about the others? Are you getting the same answer? Just rearrange the terms you have. IT is minus Cm naught tail by VH beta sorry Cl alpha tail plus I plus epsilon naught. Why are the two answers different? Why are you getting different answers? Okay, let me try solving it. Just substitute the values. What was Cm naught tail? What about the others? Are you getting the same answer or different answers? What about the others? Only two people have given the answer and they are different. I'm also getting 2.75. What about the others? How did you get 2.82 Alvin? Let me just write down the values. What have we gotten? Cm naught was minus zero point 0.2. VH was, how much was VH? 0.153. Beta is 1. Cl alpha is 0.073 plus 2 plus epsilon naught was 1.3. Is this the same value that you've used? All these terms, are these the same values? Why is epsilon naught 1.229? We got epsilon naught as 1.3, right? If I'm not wrong. Epsilon naught was 1.3, right, in the previous question? Yes. All right. Okay. So it's around minus 2.7. Okay. I hope everyone else has also followed. It's minus 2.75, but one decimal is what is given in the options. So minus 2.7. What about the others? I hope you've gotten the same answer. If you've gotten a different answer, please do let me know if we have made some mistake. But as of now, I'm going ahead with this. Okay. Next question. Okay, so a different set of data is given to you, and a different set of questions will be based on the same data. So let's look at the questions again. Weight of the aircraft is given to you, cruise velocity, the area, S, wing area, the cruise altitude, the density at the cruise altitude, density of air at the cruise altitude, aspect ratio of the wing. They've given you CG location to be the same as aerodynamic center of the wing. They've given you neutral point location. Then you have CMAC, CL characteristics of the wing and the tail. Then angle of attack, zero lift angle of attack. Just see the difference here. In the previous question, they directly given you CL naught. Here they've given you zero lift angle of attack. So you will have to find out CL naught if the question requires the value. Then they've given you wing setting angle, tail efficiency factor, horizontal tail volume ratio, yeah, Oswald's efficiency factor, tau. What was tau? Tau 0.4. What was tau? All right, okay. What was tau? So it was a control surface effectiveness parameter. Okay. Tau was control surface effectiveness parameter. Yes, tau. All right. Then you're also given delta E max. Okay, now let's look at the, yes, elevator effectiveness parameter. Correct. Okay, so he's already answered the question. The first question is, what is the lift coefficient at cruise? So you have the cruise velocity, you have what was the condition for cruise? Lift equals weight. So you can use your lift equals half rho v squared s CL equation, where lift equals weight for cruise, and you can find out CL. So if you substitute the values, what do you get? Yeah, I'm also getting 0.569. Parthiv, where did you make the mistake? So it's direct substitution, right? So CL is 2W by rho v squared S. So I am getting 0.569. What about the others? Okay. Okay. All right. So 0.569. The mistake that he had made was to not convert kgs to newtons. Please be wary of this. You need to convert it into newtons, multiply it by 9.81, and then you'll get the right answer. Next question. They've asked you to calculate downwash angle at tail in degrees. So when they said downwash angle, we should have ideally calculated epsilon, but here it's specifically said epsilon naught. I want you to calculate the epsilon naught part of it, not the entire epsilon. If that was not given, you had to do epsilon naught plus dou epsilon by dou alpha into alpha. Okay, but here they said epsilon naught, so you just have to calculate that. Again, direct substitution of formula. What was the formula? Epsilon naught was 2 CL naught by pi E A R. So try doing this, try solving this. This is where we need to find out CL naught. So they've given you zero lift angle of attack. You need to find out CL naught. So what they've given is, this is your lift curve slope, CL versus alpha. They've given that this value is minus 2 degrees. It's in degrees, okay, just assume it to be degrees. And they've given you the slope. So you need to find out CL naught. This is CL naught. Try solving this. We've gotten one answer. What about the others? What about the others? Only one answer has come. Okay, what is CL naught value? What the CL naught value? What has everyone got CL naught to be? CL naught 0.16. Okay, I'm also getting that. What about the others? What is the CL naught value? Let's solve it step by step. So what is CL naught value? From this graph, just use straight line properties and get CL naught. You have the slope, you have the zero lift angle of attack. You need to find the value at the other point. Straightforward, right? How do you do it? Is just CL naught. You just take 2 into 4.584. It's in per radian, so you need to divide it by 57 point. So divide it. 57.3, and I'm getting 0.16. Is everybody getting this? Till CL naught, is that clear? Alright. So now that you have CL naught, you just directly put it in the formula that is given there. You should be able to find out epsilon naught in degrees. Again, you'll have to make a final conversion to degrees because a value that this equation gives you will be in radians. So I'm getting 0.022 radians, and that comes to 1.16 degrees. Okay, now let's go to the next question. The value of Cm naught of the aircraft. So you need to find out Cm naught of the wing, Cm naught of the tail, and add it to get the value of Cm naught of the entire aircraft. So find it step by step. First is Cm naught wing, and then Cm naught tail, and then complete Cm naught. Cm naught is Cm naught wing plus Cm naught tail. So find it step by step. I hope you remember the formula. If not, it is fairly straightforward to derive, although it looks a little difficult. It is very straightforward to derive. You want the previous slide, Parthiv? Okay, epsilon naught. It was 1.16. So Cm naught tail, we have used this formula earlier in this class. So it was Vh beta Cl alpha tail I wing plus epsilon naught minus I tail. Okay, so this again, be careful of the units. Cl alpha tail is given to you in per radians, everything else is in degrees. What about Cm naught of the wing? What was the formula? So if you just do a basic derivation, just take the terms that are independent of angle of attack. So it was Cmac of the wing plus Cl naught into x bar Cg minus x bar AC of the wing, right? Yes, there is no elevator deflection, so you can just take it to the neutral position. Yeah, that is a fair assumption. Yes. Okay, so you have the equations for Cm naught wing and Cm naught tail. Can you tell me the values? What is Cm naught tail, Cm naught wing? And then we just need to add it up. Okay, yes. This is minus zero point 0.1. What about Cm naught tail? Okay, 0.2253. Okay, what about the others? I'm getting a different answer. I just want to see if I've made a mistake or you have. What about the other Cm naught tail? Okay, Deepashri has given the final answer D. Can you, what was your Cm naught tail value? 0.1774. Yes, I have also gotten that value. Alvin, can you just recheck your calculations? I have also got 0.1774. Let's just do it here. You can just check where you made the mistake. So VH was 0.45. Eta is zero point 0.8. Cl alpha tail is 4.0. 584, and the values are 3 plus 1.16 plus 2, and this is divided by 57.3. I'm getting something around 0.1774. I may have made a mistake, but please check and let me know. Okay, Parthiv, what was your CM0 tail value? 0.065. Okay, let me just recalculate. Maybe I have made a mistake. 0.45, 0.8. I'm getting 0.1774. Parthiv, can you recheck? I've written down the values that I've used. Can you see where you've used a different value? Converted everything in degrees. Okay, I don't think we should do that. So inherently, all of these equations are valid in radians and per radians, right? It's only when we have different values, or if the question asks for degrees, that we convert it to degrees. Inherently, all of the equations that we have are valid in radians and per radians. Just keep that in mind. Yeah, okay. CL alpha tail converted to per degrees, right? So from per radians to per degrees, you need to divide it by 57.3. Even then, the answer should be same. Yeah, so you're dividing it by 57.3. So I'm still getting 0.1774. I'm not sure how you got 0.065. Can you please recheck? I've written the values on the slide. Just cross check with your values. Oh, and Alvin, are you getting the right answer now? Are you getting the same answer? Okay, okay, all right, okay. So now I think everyone has gotten the same CM not W and CM not tail. So this is just point minus point 1 plus 0.1774, and so we get B to be the right answer. All right? Okay. I hope everybody has understood this question. Can we go to the next question? Okay, I'll just move on. Okay. Value of Cm delta E in per radians is close to. Cm delta E is dCm by d delta E. We had seen this, we introduced control just today, so I'll just write the formula. Cm delta E is minus eta VH CL alpha tail into tau. Can you tell me what value you're getting for Cm delta E? B. Okay. Okay, I'm also getting -0.66. I hope everyone has gotten that. Sorry. Okay, let's go to the next question. Static margin in cruise is close to. Static margin, you remember what it was? It was a measure of the stability of the aircraft. So, what is the static margin for this aircraft? Yes, so it's very straightforward. Static margin is the distance between the neutral point and the CG. Just subtract it, you get D, 0.22, correct. So I'll just write it for completion. It's X bar in P minus X bar CG. Okay, alright. Next question. For cruise flight, delta E required to trim the aircraft is approximately. Hope you remember the delta E formula, delta E trim formula. So assume it to be trim at the cruise. So take CL trim to be CL cruise. We had found that in the first question. Previous slide. Okay. So try to find out delta E trim. I hope you remember the formula. Do you want me? I'll just write it down anyways. So delta E trim was minus Cm naught by Cm delta E plus X bar NP minus X bar Cg by Cm delta E. Parthiv, what was your question? Okay. Oh, I thought the one before this. Okay, sorry. All right. Can I go back to the question? Yes, elevator control power, Cm delta E, correct. Elevator control power and Cm delta E are the same quantity. Is it Cl delta E or Cl alpha T? Okay, let me just go back to the. I had a slide on control. Yeah, here it is. It is Cl alpha tail. So basically, it is just Cl delta E into the moment arm, right? That is what gives you the Cm delta E. Cl alpha, delta E into the moment arm. So when you accommodate all of those changes, you get this VH parameter here with the negative sign because it is pitched down, but it is Cl alpha tail. Okay. Okay, so we were here Cl delta E trim. Cl trim. So this is the equation. You can try finding the delta E trim now. Okay, Alvin has gotten 4 minus 4.143 degrees. What about the others? Can we substitute the values? So we have minus 0.0774. We had calculated this. We had also calculated Cm delta E plus 0.22 by minus 0.66 into Cl trim is the first thing that we calculated, Cl cruise, that is 0.569, and I'm also getting minus 4.143. Okay, let's go on to the next question. Which placement of wing gives more longitudinal stability of the aircraft? High wing, low wing, mid wing, or you cannot say? So let's just take fuselage reference line and say you have a high wing configuration. So your lift and drag, lift and drag. For low wing, it will be lift and drag. So I'll just take L1, D1, sorry, D1, L2, D2. Okay, and say your CG is somewhere here. Now, using these forces, can you try and comment on the nature of stability? B. Okay. Okay, what about the others? So, Alvin, when you say more lateral stability for high wing, but I have no idea for launch. Okay, so we are only dealing with longitudinal stability for now. Look at the figure that I have drawn, and from that, can you try to justify, not justify, try to come up with an answer? So for stable aircraft, you need restoring moment, right? Okay, if you think it's the same, can you give me a justification of why you think it's the same? Correct. So Alvin's answer is the perfect justification. Drag and low wing will generate anti-clockwise moment about CG. So it gives you a restorative motion moment. So for the high wing case, both lift and drag are giving you pitch up. Both of them are giving you, uh, they are not giving you restorative moment, right? So both of them are destabilizing in nature. So both L1 and D1 give you destabilizing. They don't tend to come back to the equilibrium, but L2 and D2 are not like that. So D2 gives you a restoring moment, which is why the low wing is more stable for the longitudinal case. Does this make sense? So imagine the fuselage reference line. Is it mentioned that it is stable even in the longitudinal sense? So when you consider just longitudinal stability, I think okay. In the IGC test question, does it explicitly mention longitudinal stability or just overall stability? Okay, then I'll have to look into that because I think this justification is valid. Or do you see any problem with this justification? Do you think there is some other reason why a high wing should be more stable? Can you find some mistake with our reasoning, or can you come up with some other terms that might actually contribute towards stability in high wing for longitudinal sense? I'm also thinking I'm not able to find any reason. Can you think of any other reasons? Or if there is some mistake in our reasoning? Okay, so I'll do one thing. I'll look into it and maybe we can come visit this again in the next session. But I think our reasoning is valid, right? So I will look at the text in the book and I will get back to you. But as of now, do you think there is any mistake with our reasoning? Okay, if not, then we'll get back to this question. I'll read what's given in the book and maybe the previous year's questions, and then we'll revisit this question in the next class also. So we'll leave this for now. Okay, let's move on. Okay, a similar type of question. Which type of propeller configuration gives less longitudinal stability of the aircraft? Pusher or tractor? So a pusher is where you have the propeller at the back, right? So you have fuselage reference line. This is CG. This is pusher, and this is tractor. And say you have some angle of attack alpha. So, okay, tractor, okay, correct. So here again, some amount of lift is generated here and it is destabilizing. So tractor is less stable. Okay, so let's go to the next question. Yeah, the pitching moment coefficient versus angle of attack uh, in is given in the figure. Okay, so you have Cm and delta E. It's not angle of attack, it's Cm and delta E is given in the table. You have the Cl and Cm characteristics as equations in the question. So Cl is 0.03 plus 0.08 alpha. Cm pitching moment is 0.03 minus 0.02 alpha, where Cl is the lift coefficient of the complete airplane and alpha is in degrees. And Cm versus delta E is given in the table. Okay, so elevator control power in degrees will be D. Alright, so it's just you just find the slope. You have two values of Cm and two values of delta E. Just find the slope, and you have D. Cm delta E is 0.0031 minus 0.016 by minus 8.5 minus 1.3, and yes, D is the right answer. Go to the next question. Stick fixed neutral point x bar np, so it should be by c bar, right? And I don't know why the question details are not given. So you need to find out the stick fixed neutral point. I'll go to the previous slide for the data. Right? You need to find out stick fixed neutral point x bar np. 0.27. Are you sure? Okay, let's just try solving it. Let's go to the next slide. So static margin is minus dcm by dcl, which is also equal to x bar np minus x bar cg. So if we find out the static margin, we'll be able to find out x bar np because x bar cg is given to you in the question. So let's find out static margin. Static margin is minus, so I'll just split this ratio dcm by d alpha into 1 by dcl by d alpha. Right? We can do this and you get minus cm alpha by cl alpha. Now these two quantities are given to you directly in the question. So I'll just refer to the previous slide to get the values. Cm alpha is minus 0.02, Cl alpha is 0.08. You have 0.02 by 0.08 and you get this as 0.25. That is the static margin. Now x bar np minus x bar cg is this 0.25. So x bar np is, what was cg? It was 0.25. So x bar np is nothing but 0.5, right? Correct. Uh, were you able to find out where the mistake was made? Or have I made a mistake in the calculation somewhere? Okay, if not, I think we'll move on to the next question. Okay. The zero angle elevator trim, delta E naught in degrees will be. So we have the formula for delta E trim and the term that is independent of CL trim, that is delta E naught, the Y intercept. So delta E trim is delta E naught plus d delta E by dCl trim into CL trim, right? So this term is what they've asked you to find out, delta E naught. B. Okay, what about the others? Delta E naught is minus Cm naught by Cm delta E, right? And we have both the quantities. Cm naught is here, Cm delta E we just found out. So I'm getting 20 degrees, correct? Let's go on to the next question. The aft center of gravity limit xcg by c bar will be. Aft is the most aft, like what is the limit is the question. B, correct. So the limit till which the CG can go is the neutral point. The neutral point we've already found out to be 0.5. So that is the right answer. I hope it's clear for everyone. I think this was the last question. Which group did you send the question to, Parthiv? I don't know if I'm part of the group that you're referring to. If it's possible, can you send a link or something on this chat? We might not have time to solve it right now, but I can. I haven't gotten anything on the flight mechanics group. Yes, please. Can you just send the questions here? Alvin, what was your doubt? Yes, Parthiv, I've gotten the question. Okay. Let me try solving it. Meanwhile, Alvin, can you tell me what your doubt was? Okay. Whether the dihedral wing alone is longitudinally stable. Dihedral wing for longitudinal stability. So let's think about that. So dihedral angle is usually introduced for lateral stability. For longitudinal, it is just high and low wing configurations. And so for dihedral, it would be high wing configuration. And what we have seen right now, as far as our justification goes, high wing is not longitudinally stable, right? Which we will have to look into. So just maybe wait till the next class when if I find out whether the high wing low wing justification that we had is right. If it is right, then dihedral wing alone will not be longitudinally stable, is what I believe. Because even then it would be dihedral will be for a low wing, right? So then it might be stable. But then I will still have to check because that question is still doubtful for us. Although I believe our explanation is valid. Okay, so I will check that along with that I'll check this dihedral and let you know in the next class or in the group. I'll do the similar thing for the question that you've put in the group, Parthiv. Either I'll discuss it next session or I will try solving it and put it up in the group. Is that fine? Alvin, where have you shared? Okay. Alright, so according to this, so dihedral is usually given to a low wing, right, Alvin? So let me just. So according to our justification of the previous question, low wings are inherently longitudinally stable. So with or without the dihedral, the low wing for wing alone configuration should be stable according to our justification. So yes, dihedral would be the right answer because of that justification. The angle itself, I don't believe contributes towards any longitudinal stability as such, because the angle only produces forces, aerodynamic forces, components of forces in the lateral direction. So it contributes towards lateral stability. So only the positioning of the wing would contribute towards longitudinal stability, not the angle as such. But I will still look into it and get back. Okay, so I will get back to this question in the group or next session. Similarly for the gate question. Okay, is that fine? Okay, then we can end this session and I'll try solving this and we'll meet again in the next session. Thank you for attending the session. Thank you.